This video is about the E2 mechanism and what favors it or makes it go faster. So just like with the other mechanisms, the primary driving force behind the E2 mechanism, or which mechanism is favored, is going to be the substrate, and then also the other reactant that we're using, the reactant/reagent. So in this case, let's take a look at the substrate first. So again, substrate is usually the first thing we look at. And then for this one, we'll definitely have to look at the base strength and also the steric bulk of the base. So with the substrate, when we're looking at E2, of course we can not do an E2 if we just have a methyl, a methyl, because there's not a beta carbon, there's only an alpha carbon. And the thing we're doing with the E2 mechanism is we're making a new double bond, and so we have to have at least 2 carbon atoms. All right, next one is primary. So here would be the alpha carbon, and then this would be the beta carbon where we would remove the proton. So this would work okay. Secondary, we have the alpha carbon in here. I've made this symmetric on purpose so that we don't have to choose, we don't have to make a regiochemistry decision. We can just choose one of the beta carbon atoms to deprotonate, and they're the same. And then tertiary, again, all the same beta carbon atoms in this situation so that we don't have to make a regiochemical decision. But if we look at the transition state for this reaction, then what's happening is the leaving group is leaving. Sorry, let me draw the partial bonds out. The leaving group is leaving, so that bond's being broken. The hydrogen atom is being deprotonated by the base, so that's making a new bond there. And then a new pi bond is being made. But because this leaving group is leaving, and typically this is going to end up being something with a negative charge, especially with an E2 mechanism, you're going to have some partial positive charge buildup at the alpha carbon position in the E2 mechanism. And so because of that partial positive charge buildup, then we're actually going to get the fastest E2 with a tertiary substrate, because this will stabilize that positive charge the best. Of this series, and that's because of the fact that these alkyl groups are electron donating groups, and electron donation to something that's going to have this partial positive charge buildup is going to be more favorable. So for E2, the fastest is actually the tertiary, followed by the secondary, followed by the primary. And then we're not even going to list methyl because we can't make a pi bond with methyl. So we cannot do E2 or E1 for that matter with a methyl substrate. Next, let's look at base strength. So again, E2 like SN2 is a push mechanism. And I think of it as a push mechanism because the reactant or reagent, in this case the base we're using, is so strong that it's sort of pushing the reaction forward, and it has a lot of potential energy and it's pretty high energy base. So that's going to help push the reaction forward. So here we need a strong base. And typically we're going to see, when we talk about strong bases, we always mean hydroxide or stronger, OH negative, OR negative, and alkoxide. Any sort of amide anion would be very strong and strong enough. Hydride anion technically. And those are going to be probably the primary ones we're going to see with E2. There are a couple of special ones that we use a lot with E2. And one of those is potassium tert butoxide. So you'll see this written KOT-bu. Or sometimes you'll see it written out with the condensed formula. CCH3, 3, something like that. But what this is going to be is a strong, bulky base. And in the in the regiochemistry video, we talk about this. This is going to encourage the Hoffman product, which is going to be the less substituted alkene product. And that's because it's so bulky that it makes it hard to get into the proton to make the more substituted alkene. Also, when we have these strong bulky bases like this is also going to encourage E2 over SN2 with these particularly. The other very strong, in this case very strong bulky base is something abbreviated LDA. You'll see this one a lot, so this is one worth knowing. It's worth putting on a note card. So it stands for lithium diisopropyl amide. So that's the anion part, and of course the cation part is this one. And this would be a very strong bulky base. But this is going to do the same thing in this reaction at least. Other reactions, these two are going to do different things because of the difference in strength. But for the E2 mechanism, this one is also going to tend to give you the Hoffman product. And these are also going to cause E2 to be favored over SN2, even with primary substrates. And that's because of that bulk. Because we remember with SN2, the nucleophile has to get all the way into the electrophilic carbon atom. And with these bulky bases, that's going to be really hard for them to do. And also proton transfer is just going to be faster. So with these, even if you see a primary substrate, if you see tert butoxide or LDA, you're going to do E2, and you're also going to make sure it's the Hoffman product. All right, so that's substrate and base strength. The other factors, of course, are temperature. And we talked about this in another video, but basically, because of the Gibbs free energy equation, the entropy is going to play a factor here. So with higher temperatures, when we have a delta S that's larger, that's going to encourage that reaction. And in fact, with the E2 mechanism, or with either elimination mechanism, we end up with the conjugate base, the conjugate acid of the base, and the alkene, and then we have the leaving group. So we start out with 2 molecules, and we end up with 3 molecules. And so higher temperature is going to favor elimination in general. And of course, lower, more moderate temperatures is going to help favor SN2. A lot of times you won't see the higher temperature listed in the reactions we're doing, especially a lot of times with E2, you'll see a secondary substrate that has one of these good bases, and they'll put the E2 mechanism as being favored over SN1, over SN2. And that may be the case even at more moderate temperatures. But if you were trying to do this in a synthesis, you would be trying to, push it the direction you want it to go, because you don't want to get a lot of a product that is not the product you're interested in. So in real life, you would probably end up heating the elimination to try to really encourage elimination over substitution, unless you wanted substitution, and then you would choose a lower or more moderate temperature. The last thing is solvent. So with the solvents here, technically a polar aprotic would be the best, because it's not going to get in the way of the base or react with the base, and also it's not going to, or it's going to help stabilize that positive charge buildup in the transition state. However, a lot of times what you'll see is you'll still see polar protic solvents. And the reason for that is because a lot of the times you'll see where they're making the alkoxide directly from the alcohol, and then they're using that alcohol as a solvent. So for example, let's say we were doing this and we had a good leaving group. We had tosylate as my leaving group, and then you might see where they're using sodium ethoxide and they're using ethanol as the solvent. And here especially, they might not even say that they're heating it. Again, in real life, we would probably heat it to make sure it worked well. But because we see here tertiary substrate, and we know that goes best, or that's the fastest with E2 for E2, and wouldn't work at all very well with SN2, we see we have a strong base. And what they've done here most likely is they put in maybe a strong base to deprotonate the ethanol and made the ethoxide in situ. So what we'll have here is, of course, the elimination reaction. And we'll make ethanol as the byproduct and the tosylate anion as the other byproduct. So that's it. So tertiary is fastest with E2. We need a strong base. If that strong base is one of our bulky bases, we're really going to favor E2 over SN2, even with a tertiary substrate, and we're also going to get that Hofmann. Higher temperature is going to favor elimination in general, E1 and E2. And while a solvent, polar aprotic solvent is the best, you will often see polar protic solvents used, such as the alcohol conjugate acid of the base that's being used.